Dear students, welcome to EPG Pathshala. I am Dr. Rajkishore Sharma, working as an Associate Professor in Department of Chemistry, University of Delhi. Today, we are going to discuss about the module Introduction of Photoelectron Spectroscopy. This is under the paper of Surface Analytical Techniques 2. The main goal of photoelectron spectroscopy is to gain information about the composition, electronic state, chemical state, binding energy, and more on the surface region of solids. Lot of qualitative and quantitative information can be learned about the surface region of solids. Specifics about what can be studied using PES or photoelectron spectroscopy will be discussed in details in the following discussion on instrumentation over PES experiments. The topic that we are going to discuss today, we will start with introduction, then move on to ionization energy, factors on which ionization energy depends, Kopman's theorem, type of photoelectron spectroscopy, then we'll discuss about ultraviolet photoelectron spectroscopy, X-ray photoelectron spectroscopy, and at the end we will discuss about photoelectric effect. The photoelectron spectroscopy, also known as PES or photoemission spectroscopy, refers to the energy measurements of electrons emitted from solids, liquids, or gases by the photoelectric effect. In order to determine the binding energies of an electron in a substance, the term refers to various techniques depending on whether the ionization energy is provided by an X-ray photon or an ultraviolet photon. Regardless to the incident photon beam, however, all the photoelectron spectroscopies revolves around the general theme of surface analysis by measuring the ejected electrons. It is an experimental method used to determine the electronic structure of atoms and molecules. It detects the kinetic energy of electron escaped from the surface. It utilizes photoionization and analysis of the kinetic energy distribution of the emitted photoelectrons to study the composition and electronic state of the surface region of a sample. Photoelectron spectroscopy is based on Einstein's photoelectric principle. The photoelectric effect is the emission of electrons or other free carriers when light is shined on a material. Electrons emitted in this manner can be called photoelectrons. A photoelectron ionizes an electron from a molecule if the photon has energy greater than the energy holding of the electron in molecule. Any photon energy in excess of that needed for ionization is carried out by the outgoing electron in the form of kinetic energy. In photoelectron spectroscopy, photons of well-defined energy are absorbed in a sample by the process of electron excitation. Provided the photon energy h nu is high enough, that is few hundreds or few tens of electron volt in case of X-rays or UV source of light respectively. Provided the photon energy h nu is high enough, atoms within the irradiated sample volume may be excited above the ionization threshold or the work function in case if the specimen is a solid sample. Ejected electron flux is measured as a function of their kinetic energy by means of an electron energy analyzer, thus obtaining an intensity versus energy curve, that is energy distribution curve, commonly known as EDC. The EDC gives information on the core level, the initial state energy and the band structure. Now we will discuss briefly about photoelectron spectrometer. It consists of a light source, an electron gun, energy analyzer, high vacuum environment and an electron detector. Light source, for XPS, it is an X-ray source And for UPS, it is helium discharge lamp, an electron gun. It is used for detailed study of inelastic electron scattering and for creating inner shell vacancies. The energy analyzer, it can disperse the emitted electrons according to their kinetic energy and thereby measure the flux of emitted electrons of a particular energy. Next is the high vacuum environment. It is used to enable the emitted photoelectrons to be analyzed without interference from gas phase collisions. Photoelectron spectroscopy is rather picky when it comes to keeping the surface of the sample clean and keeping the rest of the environment free of interferences from such things like gas molecules. The high vacuum is almost always an ultra high vacuum, that is UHV environment. Last is an electron detector. It detects and counts the number of electrons. Now we will discuss briefly about photoelectron spectra. The plots of photoelectron counts versus binding energy or BE is known as photoelectron spectra. In photoelectron spectrum, binding energy is usually expressed in kilojoules, megajoules or electron volts per mole. More binding energy implies the electron resides in lower subcells, that is, the electrons that are closer to nucleus experience more force of attraction and therefore require more energy to remove. We will discuss about the ionization energy. If you look back in your textbook of chemistry, you will most likely find a table in the appendix that lists the various ionization energies or ionization potentials. For most of elements on the periodic table, the ionization energy is how much energy is required to remove an electron from a neutral atom in the gaseous phase and typically has units of kilojoules or electron volts per mole. It is also known as binding energy. It is determined by photoelectron spectroscopy. Ionization energy, or we write in short IE, is defined as the amount of energy required to remove the most loosely bound electron, that is the valence electron, of an isolated gaseous atom to form a cation. It provides some of the most detailed quantitative information about electronic structure of organic and inorganic molecules. We can write the X plus energy. X is a gaseous atom, plus energy is X plus, that is ionized atom, plus electron. Here X is any gaseous atom capable of being ionized. The first ionization energy is the energy required to remove 1 mole of the most loosely held electron from 1 mole of gaseous atom to produce 1 mole of gaseous ion, each with a charge of +1. We can write X plus energy is X plus an electron. This is called first ionization energy. Now about the second ionization energy. It is the energy needed to remove a second electron from each ion in 1 mole of gaseous 1 plus ions to give gaseous 2 plus ions. So in the form of an equation we can write X plus energy. It gives X2 plus electron and is termed as second ionization energy. The third ionization energy is defined as the energy needed to remove the third electron from an atom. It gets progressively more difficult to remove electrons, and so we see that the first ionization energy is less than the second ionization energy, which is less than the third ionization energy. third ionization in the form of an equation can be written as X2 plus energy, that is the third ionization energy. It gives X3 plus the electron. The factors on which ionization energy depends. This is number one is the size of atom. The ionization energy depends upon the size of atom because the increase in size, the distance between nucleus and valence electrons increases, and hence force of attraction between nucleus and valence electron decreases, as a result of which the valence electrons are loosely held and smaller energy is required to remove an electron. Therefore, the ionization energy decreases with increase in size and increase with decrease in size. Now, about the nuclear charge. As the nuclear charge increases, the force of attraction between nucleus and valence electrons increases, and hence it is difficult to remove an electron from valence shell. Thus, with increase in nuclear charge, the ionization energy increases. Now, the screening effect or shielding effect. The inner electrons present in the shells between nucleus and valence shells reduce the attraction between nucleus and the outermost electrons. This shielding effect depends upon the number of inner electrons. Larger the number of electrons in the inner shell, the greater is the screening effect. More the shielding effect, easier will be to remove an electron, and hence lesser will be the ionization energy. Now, the penetration effect. S electrons are closer to the nucleus than P electrons, which is closer than D electrons, and thus in turn are closer than F electrons of the same principal energy level. Hence, S electrons experience more attraction from the nucleus than P, D and F electrons. Thus, ionization energy to remove an electron from a given energy level decreases in order S is greater than P is greater than D is greater than F. Now, about the electronic configuration. Electronic configuration plays a vital role in determining the value of ionization energy. Atoms having stable configuration, that is fully filled or half filled, has least tendency to lose electrons and hence have high value of ionization energy. The Kopman's theorem. Kopman's theorem states that the negative of the eigenvalue of an occupied orbital from a Hartree-Fock calculation is equal to the vertical ionization energy to the ion state found by removal of an electron from that orbit, provided the distributions of the remaining electron do not change. In other words, we can say that Kopman's theorem states that the first ionization energy of a molecule is equal to the negative of the energy of the highest occupied molecular orbital. Kopman's theorem uses the Hartree-Fock method for approximation of orbital energy, that is eta I, which is derived from the wave function of the spin orbital and the kinetic energy and nuclear attraction energies. This theorem applies when an electron is removed from a molecular orbital in order to form a positive ion. It was originally only used for ionization energies in a closed cell system, but has been generalized to be used to calculate energy changes when electrons are added or removed from a system. Based on this generalization, it is possible to use the same method to approximate the electron affinity. Just for general information, Kopmans became Nobel laureate in 1975, though neither in physics nor in chemistry, but in economics. The type of photoelectron spectroscopy. Underneath the banner of photoelectron spectroscopy are two separate techniques for quantitative and qualitative measurements. They are ultraviolet photoelectron spectroscopy, in short it is called as UPS, and X-ray photoelectron spectroscopy, which is abbreviated as XPS. XPS is known under its former name of electron spectroscopy or chemical analysis ESCA. UPS focuses on ionization of valence electron, while XPS is able to go a step further and ionize core electron and pry them away. Ultraviolet photoelectron spectroscopy. This spectroscopy refers to the measurement of kinetic energy spectra of photoelectrons emitted by molecules which have absorbed ultraviolet photons in order to determine molecular orbital energies in the valence region. We will have a quick look on the history. UPS was developed originally for gas phase molecules in 1962 by David W. Turner, and other early workers included David C. Frost, J. H. D. Allen, and K. Kimura. Later, Richard Smalley modified the technique and used a UV laser to excite the sample in order to measure the binding energy of electrons in gaseous molecular clusters. The advantages of UPS, ultraviolet photoelectron spectroscopy. The ultraviolet radiation has a very narrow line width and a high flux of photons available from simple discharge sources. High resolution UPS scans allow for the observation of the fine structures that are due to vibrational levels of the molecular ions, which then allows molecular orbital assignment of specific peaks. There is one limitation of UPS also. UPS is capable only of ionizing valence electrons. That limits the range and depth of UPS surface experiments. Conventional UPS has relatively poor resolution. Specific examples of UPS studies include: number 1, the measurement of molecular orbital energies that can be compared to theoretical values calculated from quantum chemistry. Number 2, determination and assignment of bonding, non-bonding and or anti-bonding molecular orbitals. Number 3, the binding and orientation of adsorbed species on the surface of solids. Fourth and the last is band structure mapping in K-space with angle resolved techniques. Now, the application of ultraviolet photoelectron spectroscopy. The measurement of molecular orbital energies that can be compared to theoretical values calculated from quantum chemistry. The high resolution allowed the observation of fine structures due to vibrational levels of the molecular ion, which facilitates the assignment of peaks of bonding, non-bonding and anti-bonding molecular orbitals. Useful results from characterization of solids by UPS or ultraviolet photoelectroscopy is the determination of work function of the material. UPS spectra are obtained by irradiating a material with an ultraviolet beam with simultaneously measuring the kinetic energy and number of electrons that escape from the material is being analyzed. Since valence electrons reside in the outermost shell, they experience less force of attraction from the nucleus and therefore they require less energy for ejection. For reference, the photon energy of 10 to 45 electron volt. In early UPS, the sample was a gas or a vapor that is irradiated with a narrow beam of UV radiation. Modern UPS instruments are now capable of studying solids as well. The photoelectrons produced are passed through a slit into a vacuum region where they are then deflected by magnetic or electrostatic fields to give an energy spectrum. The schematic of the UPS mechanism is shown in the slide. As it is shown in the slide, when UV light is irradiated on the sample, the valence electrons are ejected out. UPS is sensitive to the very near surface region up to around 10 nanometer in depth. Now we will discuss about the X-ray photoelectron spectroscopy. It is a surface sensitive, quantitative spectroscopic technique that measures the chemical composition at the part per thousand range, empirical formula, chemical state and electronic state of the element that exists within a material. X-ray spectra are obtained by irradiating a material with a beam of X-rays while simultaneously measuring the kinetic energy and number of electrons that escape from the top 0 to 10 nanometer of the material being analyzed. XPS requires high vacuum that is in the order of 10 to the power minus 10 millibar, or ultra high vacuum UHV, which is less than 10 to the power minus millibar conditions. XPS is extremely good for surfaces. This is because the kinetic energy of escaping photoelectron limits the depth able to be probed. The samples studied are all solids for some type, ranging from metals to frozen liquids. When the sample is irradiated, the electrons ejected are from the inner shells of the atoms. There are several areas suited to measurement by XPS. Number 1, the elemental composition of material can be found out using XPS. It is helpful in determining the empirical formula. It helps in estimating the chemical state of a material. It is useful for the electronic state as well. It gives precise binding energy in a material, and the layer thickness in the upper portion of the surfaces can be found out using depth profiling technique. Some specific examples of systems studied by XPS are: number 1, the analysis of strain and residues on surfaces. Number 2, reactive frictional wear of solid-solid reactions. Number 3, silicon oxynitride thickness and measurement of dosage. The 4th, depth profiling. In depth profiling, a sputter source is used. This removes successive layers from the surface of a sample and allows for the quantification of element depth profile that to be recorded in the near surface region. This is useful in the composition of thin films. Now, angle dependence measurement. When the angle of measurement is changed, the depth of information gathered can be varied by 1 to 10 nanometer. The usefulness here is in determining the concentration of additives in the surface region. Now, imaging of the surfaces. Utilizing a special imaging mode, the distribution of elements in surface structure can be determined. This technique is useful in dimensions up to about 3 micrometer. Now, the spectral output. Briefly, the spectrum from an XPS experiment is a graph of emission intensity versus binding energy. This allows identification of elements on the surface, and it is based on the unique binding energy of each element. The peak areas on these spectra can also be used to obtain the concentration of the element on the surface as well. Detailed information on the interpretation of XPS spectra is planned for a subsequent module. The PES technique is based on the photoelectric effect. The photoelectric effect was first observed in 1887 by Heinrich Hertz. During experiments with a spark gap generator, it was the earliest form of radio receiver. In these experiments, a spark is generated between two small metal spheres in the transmitter to introduce a similar spark to jump between two different metal spheres in the receiver. Compared to later radio device, the spark gap generator was notoriously difficult to work with. The air gap would often have to be smaller than a millimeter for a receiver to consistently reproduce the spark of the transmitter. Hertz found that he could increase the sensitivity of his spark gap device by illuminating it with the visible or ultraviolet light. Later studies by J.J. Thomson showed that this increased sensitivity was the result of light pushing on electrons, which he discovered in 1987. It was Philip Lenard, an assistant of Hertz, who performed the earliest definitive studies of the photoelectric effect. Lenard used metal surfaces that were first cleaned and then held under a vacuum so that the effect might be studied on the metal alone and not be affected by any other surface contaminants or oxidation. The metal sample was housed in an evacuated glass tube with a second metal plate mounted on the opposite side. The tube was then positioned or constrained in some manner so that light would only shine on the first metal plate, the one made out of the photoemission material under investigation. Such a tube is called photocell or an electric eye. Photocell was formal name. electric eye was called informally. Lenard connected his photocell to a circuit with a variable power supply, voltmeter, and a microammeter as shown in the schematic diagram above. He then illuminated the photoemissive surface with light of different frequencies and intensities. The photoelectric effect is the emission of electrons or other free carriers when light is shown onto a material. Electrons emitted in this manner can be called photoelectrons. Photoemission can occur from any material, but it is most easily observable from metals or other conductors because the process produces charge imbalance. And if this charge imbalance is not neutralized by current flow, the potential barrier to emission increases until the emission current ceases. Now, the emission mechanism. As we know that the photons of a light beam have a characteristic energy which is proportional to the frequency of light. In the photoemission process, if an electron within some material absorbs the energy of one photon and acquire more energy, then the work function is the electron binding energy of the material is ejected. If the photon energy is too low, the electron is unable to escape the material. Since an increase in the intensity of low frequency light will only increase the number of low frequency photons sent over a given interval of time, the change in intensity will not create any single photon with the enough energy to dislodge an electron. Thus, the energy of the emitted electron does not depend on the intensity of incoming light, but only on the energy, that is equivalent frequency, of the individual photons. It is an interaction between the incident photon and the outermost electrons. Electrons can absorb energy from photons when irradiated, but they usually follow an all or nothing principle. All of the energy from one photon must be absorbed and used to liberate one electron from atomic binding, or else the energy is re-emitted. If the photon energy is absorbed, some of the energy liberates the electron from the atom, and the rest contributes to the electron's kinetic energy as a free particle. The energy of a photon of all types of electromagnetic radiation is given by Einstein's relation, that is h nu. E is equal to h nu. It is a simple relation Einstein gave. Here h is the Planck's constant, whose value is 6.62 into 10 raised to the power minus 34 joule second. Nu is the frequency in hertz of the radiation. Here in XPS, the photon is absorbed by an atom in a molecule or solid, leading to ionization and emission of a core inner shell electron. By contrast, in UPS, the photons interact with valence levels of molecule or solid, leading to ionization by removal of one of these valence electrons. Now, we will summarize what we have learned today in this module. PES, or photoelectron spectroscopy, refers to the energy measurement of electrons emitted from solids, liquids or gaseous substances by the photoelectric effect, in order to determine the binding energies of an electron in a substance. Photoelectron spectroscopy is based on Einstein's photoelectric effect. Ionization energy is defined as the amount of energy required to remove the most loosely bound electron, that is the valence electron of an isolated gaseous atom, to form a cation. It provides some of the most detailed quantitative information about electronic structure of organic and inorganic molecules. Underneath the banner of PES, these are two separate techniques for quantitative and qualitative measurements. One is ultraviolet photoelectron spectroscopy, that is UPS, and other is the X-ray photoelectron spectroscopy, called XPS. UPS focuses on ionization of valence electrons, while XPS is able to go to a step further and ionizes core electrons and pry them away. UPS spectra are obtained by irradiating a material with an ultraviolet beam while simultaneously measuring the kinetic energy and number of electrons that escape from the material being analyzed. XPS spectra are obtained by irradiating a material with a beam of X-rays while simultaneously measuring the kinetic energy and number of electrons that escape from the top 0 to 10 nanometer of the material being analyzed. The photoelectric effect is the emission of electrons or other free carriers when light is shined onto a material. Electrons emitted in this manner can be called the photoelectrons. Thank you.